Let's talk about the combined stress formula. What the combined stress that we're going to be talking about is exactly what we talked about with the pre-stressed concrete example. We're going to be talking about an axial stress plus a bending stress. Okay, that's very common in, like I say, a lot of our civil type applications. And I'll try to note a few of the cases that this occurs at. It, of course, occurs when we're talking about a pre-stressed beam. I should mention there's also, in addition to a pre-stressed beam, there's what's referred to as a post-tension beam, which, or post-tension element, which, again, you can actually do the tensioning of the cable. You can do that out in the field as well, too. And you'd be doing it after, like, you pour the concrete, and they'd have little, like, sheaths or little tubes that the cable would actually reside in. So, but it's post-tensioning from a standpoint of how it operates is really technically just about the same as pre-stressing. For stresses, the purposes we're talking about, it can be considered the same. Anyway, the combined stress formula. The generic formula might be something like this. Combined stress is equal to the direct stress, P over A, plus or minus the bending stress, MC over I. Okay? And why do you think we say plus or minus there? Well, we say plus or minus because the direct stress is always either going to be tension or compression. We know that. I mean, when we're in a given situation, we have a problem in front of us, we're going to know what the direct stress is. It's either going to be tension or compression. So we'll know that. When we talk about bending stress, a bending stress is both tension and compression at the same time. Remember, when we have a beam type element, those beams have tension stress on one side and compression stress on the other side. And so when you're talking about bending, it happens at the same time. I mean, this is a fine and dandy formula for you. What I like doing is I like just saying P over A plus MC over I. And then what I like to do is I like to say anytime you have a tension stress, we're going to call that positive, and anytime you have a compression stress, you're going to call that negative. Okay? So, you know, let's say we had direct stress and it was tension. Okay? What I'd be saying is plus the direct stress, and then when I had a tension, when I was looking at the tension side of the element, I'd be saying plus. So the combined stress would be plus because I had tension due to direct stress, and plus because I had tension on the side of the element that I had tension. On the other side of the element, you know, the bending stress is going to be now compression. And so that's when I'd say plus minus, you know, the bending stress. Okay? So in here, I'll always call tension, no matter if it's from direct stress or bending stress, I'll always call tension positive. That's just, you don't have to do it that way, but that's what I'll do. Okay? Now, how does this really work? You know, I mean, we know this formula. We've calculated P over A, you know, 3 dozen times already in the last couple weeks. We've calculated MC over I, you know, hopefully a dozen times or so over the last week. How do these things just add or subtract, as the case may be? How does it add or subtract? Well, here's why. Let's say I had a beam, all right? That beam, let's just say I had a tension force on it. You know, that would mean I'd have a tension stress that, and again, we talked about P over A being sort of an average, being a uniform average over the whole cross section, right? Well, if I add to that a bending stress, we talked last week how bending stress would be tension on one side, but compression on the other side, right? Well, let's look at the bottom part of the beam. If this was the bottom part of the beam and I said, hey, I had 100 psi due to the tension stress, and I had 200 psi due to the in tension due to the bending stress on that side of the beam, what would these two stress vectors combine to be? I got 100 psi in tension going that way. I got 200 psi in tension going that way. What would they combine to be? 300, right? What about the other side of the beam? If I had 100 psi tension going that way, the other side of the beam, it would have to be the same, right, if this was a symmetrical, homogeneous type beam. So, but it would be 200 psi in compression. So what did I just say? Tension's going to be what? Positive. So I got plus 100. What's compression going to be? Negative 200. Plus 100 minus 200. What do I end up with on this side of the beam? Negative 100 or 100 compression. Okay? So here's what my distribution would look like. Okay? What would it be right at the mid-depth of the beam? What would I have? I'd have 100 plus what? 0. So right at mid-depth of the beam, I'd have 100 psi tension. You see how that works? It's a real, I mean, it's real straightforward because all these stress vectors are collinear. What do you think the number one thing is to try to keep straight when you're doing this, besides signs, tension and compression and whatnot? What do you think the number one thing is to keep straight? Probably units again. You know, you know, if this is PSI, you want to make sure you're adding PSI to it. All right. So really, I'd say the number one thing is make sure you've got your, especially with bending, you understand which side of the beam's in tension or which side of the element's in compression. You know, the other thing though is to really pay attention to units because that's going to be important.